Chapter 2. Atoms and Electrons. Objectives. 1. Understand the wave-particle duality of nature in quantum mechanics. 2. Study the Bohr model of atoms. 3. Apply the Schrödinger equation to simple problems. 4. Understand the electronic structure of atoms and the periodic table. 5. Understand how semiconductor properties are determined. Since this book is primarily an introduction to solid-state devices, it would be preferable not to delay this discussion with subjects such as atomic theory, quantum mechanics, and electron models. However, the behavior of solid-state devices is directly related to these subjects. For example, it would be difficult to understand how an electron is transported through a semiconductor device without some knowledge of the electron and its interaction with the crystal lattice. Therefore, in this chapter we shall investigate some of the important properties of electrons, with special emphasis on 2 points: 1. The electronic structure of atoms, and 2. The interaction of atoms and electrons with excitation, such as the absorption and emission of light. By studying electron energies in an atom, we lay the foundation for understanding the influence of the lattice on electrons participating in current flow through a solid. Our discussions concerning the interaction of light with electrons form the basis for later descriptions of changes in the conductivity of a semiconductor with optical excitation, properties of light-sensitive devices, and lasers. First, we shall investigate some of the experimental observations which led to the modern concept of the atom, and then we shall give a brief introduction to the theory of quantum mechanics. Several important concepts will emerge from this introduction. The electrons in atoms are restricted to certain energy levels by quantum rules. The electronic structure of atoms is determined from these quantum conditions, and this quantization defines certain allowable transitions involving absorption and emission of energy by the electrons. The main effort of science is to describe what happens in nature, in as complete and concise a form as possible. In physics, this effort involves observing natural phenomena, relating these observations to previously established theory, and finally establishing a physical model for the observations. For example, we can explain the behavior of a spring-supported weight moving up and down periodically after an initial displacement, because the differential equations describing such a simple harmonic motion have been established by Newtonian classical mechanics. When a new physical phenomenon is observed, it is necessary to find out how it fits into the established models and laws of physics. In the vast majority of cases, this involves a direct extension of the mathematics of well-established models to the particular conditions of the new problem. In fact, it is not uncommon for a scientist or engineer to predict that a new phenomenon should occur before it is actually observed, simply by a careful study and extension of existing models and laws. The beauty of science is that natural phenomena are not isolated events but are related to other events by a few analytically describable laws. However, it does happen occasionally that a set of observations cannot be described in terms of existing theories. In such cases, it is necessary to develop models which are based as far as possible on existing laws, but which contain new aspects arising from the new phenomena. Postulating new physical principles is a serious business, and it is done only when there is no possibility of explaining the observations with established theory. When new assumptions and models are made, their justification lies in the following question: does the model describe precisely the observations, and can reliable predictions be made based on the model? The model is good or poor depending on the answer to this question. In the 1920s, it became necessary to develop a new theory to describe phenomena on the atomic scale. A long series of careful observations had been made that clearly indicated that many events involving electrons and atoms did not obey the classical laws of mechanics. It was necessary, therefore, to develop a new kind of mechanics to describe the behavior of particles on this small scale. This new approach, called quantum mechanics, describes atomic phenomena very well and also properly predicts the way in which electrons behave in solids. Our primary interest here. Through the years, quantum mechanics has been so successful that now it stands beside the classical laws as a valid description of nature. A special problem arises when students first encounter the theory of quantum mechanics. The problem is that quantum concepts are largely mathematical in nature and do not involve the common sense quality associated with classical mechanics. At first, many students find quantum concepts difficult, not so much because of the mathematics involved, but because they feel the concepts are somehow divorced from reality. This is a reasonable reaction, since ideas which we consider to be real or intuitively satisfying are usually based on our own observation. Thus the classical laws of motion are easy to understand because we observe bodies in motion every day. On the other hand, we observe the effects of atoms and electrons only indirectly, and naturally we have very little feeling for what is happening on the atomic scale. It is necessary, therefore, to depend on the facility of the theory to predict experimental results rather than to attempt to force classical analogues onto the non-classical phenomena of atoms and electrons. Our approach in this chapter will be to investigate the important experimental observations that led to the quantum theory, and then to indicate how the theory accounts for these observations. Discussions of quantum theory must necessarily be largely qualitative in such a brief presentation, and those topics that are most important to solid-state theory will be emphasized here. Several good references for further individual study are given at the end of this chapter. The experiments that led to the development of quantum theory were concerned with the interaction of light and matter. On the one hand, there were phenomena such as interference or diffraction which clearly indicated that light has a wave character as proposed by Huygens, in contrast to the particle or corpuscular view of light proposed by Newton. But on the other hand, many experiments at the turn of the 20th century clearly showed that a new theory of light was needed. The photoelectric effect. An important observation by Planck indicated that radiation from a heated sample, known as blackbody radiation, is emitted in discrete units of energy called quanta. The energy units were described by Hn, where n is the frequency of the radiation, and h is a quantity now called Planck's constant, h equals 6.63 * 10 to 34 J at s. Soon after Planck developed this hypothesis, Einstein interpreted an important experiment that clearly demonstrated the discrete nature, quantization, of light. This experiment involved absorption of optical energy by the electrons in a metal and the relationship between the amount of energy absorbed and the frequency of the light, Fig. 2.1. Let us suppose that monochromatic light is incident on the surface of a metal plate in a vacuum. The electrons in the metal absorb energy from the light, and some of the electrons receive enough energy to be ejected from the metal surface into the vacuum. This phenomenon is called the photoelectric effect. If the energy of the escaping electrons is measured, a plot can be made of the maximum energy as a function of the frequency n of the incident light, Fig. 2.1b. One simple way of finding the maximum energy of the ejected electrons is to place another plate above the one shown in Fig. 2.1a and then create an electric field between the two plates. The potential necessary to retard all electron flow between the plates gives the energy m. For a particular frequency of light incident on the sample, a maximum energy m is observed for the emitted electrons. The resulting plot of m versus n is linear, with a slope equal to Planck's constant. The equation of the line shown in Fig. 2.1b is, where q is the magnitude of the electronic charge. The quantity, volts, is a characteristic of the particular metal used. When is multiplied by the electronic charge, an energy, joules, is obtained which represents the minimum energy required for an electron to escape from the metal into a vacuum. The energy Q is called the work function of the metal. These results indicate that the electrons receive an energy Hn from the light and lose an amount of energy Q in escaping from the surface of the metal. This experiment demonstrates clearly that Planck's hypothesis was correct. Light energy is contained in discrete units rather than in a continuous distribution of energies. Other experiments also indicate that, in addition to the wave nature of light, the quantized units of light energy can be considered as localized packets of energy, called photons. Interestingly, this is reminiscent of the Newtonian picture. We get the Planck relationship. the photoelectron energy was found not to increase with increasing light intensity, instead the number of photoelectrons increases. This is in sharp contrast to what classical physics would have predicted. A higher amplitude or intensity wave packs more energy, and should have increased the photoelectron energy. Instead, we find in quantum physics that a higher intensity light corresponds to a larger number of these photons, and hence a larger number of photoelectrons. Some experiments emphasize the wave nature of light, while other experiments reveal the discrete nature of photons. This wave-particle duality is fundamental to quantum processes and does not imply an ambiguity in the theory. This duality is seen beautifully in the Young's double-slit diffraction experiment. We may recall that if monochromatic light is shown through two narrow slits onto a screen, we see diffraction and interference patterns on the screen corresponding to high-intensity bright regions, constructive interference, and low-intensity dark regions, destructive interference. This is consistent with the wave picture. Now, if the intensity of the light source is reduced, so that just a few photons are emitted per second, we find that we do not get an interference pattern. Instead, we get specks of light wherever the photon hits the screen, because a photon cannot be split. There is a certain amount of randomness in terms of where the photon hits. However, if we continue with the experiment, these random hits of the photons gradually build up the interference pattern, corresponding to the wave picture. Statistically, there are more photon hits in the bright regions of the screen, and fewer hits in the dark spots. Similar results were subsequently observed with electrons and other subatomic particles. This wave-particle duality is fundamental to the development of quantum mechanics. Hence, based on the wave-particle duality of light, Louis de Broglie proposed that particles of matter, such as electrons, similarly could manifest a wave character in certain experiments. This observation was confirmed by the diffraction of electrons by the periodic array of atoms in a crystal observed by Davison and Germer. De Broglie proposed that a particle of momentum p equal mv has a wavelength given by. The Planck and de Broglie relationships are fundamental in quantum physics and are valid for all situations and objects, including photons and electrons. They connect the wave description of phenomena, frequency and wavelength, to a particle description, energy and momentum. The relation between frequency and wavelength, or equivalently, energy and momentum, known as the dispersion relationship, however, is not the same for different objects. For example, for photons, the wavelength, L, is related to frequency by, where c is the speed of light. For electrons, it is an approximately parabolic dispersion relationship, E, K, also known as the band structure, as discussed in Chapter 3. Atomic spectra. One of the most valuable experiments of modern physics is the analysis of absorption and emission of light by atoms. The de Broglie wave property of electrons is key to understanding these experiments. For example, an electric discharge can be created in a gas, so that the atoms begin to emit light with wavelengths characteristic of the gas. We see this effect in a neon sign, which is typically a glass tube filled with neon or a gas mixture, with electrodes for creating a discharge. If the intensity of the emitted light is measured as a function of wavelength, one finds a series of sharp lines rather than a continuous distribution of wavelengths. By the early 1900s the characteristic spectra for several atoms were well known. A portion of the measured emission spectrum for hydrogen is shown in Fig 2.2, in which the vertical lines represent the positions of observed emission peaks on the wavelength scale. Photon energy Hn is then related to wavelength by the dispersion relation L equals C/n. The lines in Fig 2.2 appear in several groups labeled the Lyman, Balmer, and Paschen series after their early investigators. Once the hydrogen spectrum was established, scientists noticed several interesting relationships among the lines. The various series in the spectrum were observed to follow certain empirical forms. Where R is a constant called the Rydberg constant, R equal 109,678 cm, 1. If the photon energies Hn are plotted for successive values of the integer n, we notice that each energy can be obtained by taking sums and differences of other photon energies in the spectrum, Fig 2.3. For example, E42 in the Balmer series is the difference between E41 and E21 in the Lyman series. This relationship among the various series is called the Ritz combination principle. Naturally, these empirical observations stirred a great deal of interest in constructing a comprehensive theory for the origin of the photons given off by atoms. The results of emission spectra experiments led Niels Bohr to construct a model for the hydrogen atom, based on the mathematics of planetary systems. If the electron in the hydrogen atom has a series of planetary-type orbits available to it, it can be excited to an outer orbit and then can fall to any one of the inner orbits, giving off energy corresponding to one of the lines of Fig 2.3. To develop the model, Bohr made several postulates. 1. Electrons exist in certain stable, circular orbits about the nucleus. This assumption implies that the orbiting electron does not give off radiation as classical electromagnetic theory would normally require of a charge experiencing angular acceleration, otherwise, the electron would not be stable in the orbit but would spiral into the nucleus as it lost energy by radiation. 2. The electron may shift to an orbit of higher or lower energy, thereby gaining or losing energy equal to the difference in the energy levels, by absorption or emission of a photon of energy Hn. 3. The angular momentum pW of the electron in an orbit is always an integral multiple of Planck's constant divided by 2p, H2p is often abbreviated U for convenience. This assumption is necessary to obtain the observed results of Fig 2.3. Although Bohr proposed this ad hoc relationship simply to explain the data, one can see that this is equivalent to having an integer number of de Broglie wavelengths fit within the circumference of the electron orbit. These were called pilot waves, guiding the motion of the electrons around the nucleus. The de Broglie wave concept provided the inspiration for the Schrödinger wave equation in quantum mechanics discussed in section 2.4. If we visualize the electron in a stable orbit of radius r about the proton of the hydrogen atom, we can equate the electrostatic force between the charges to the centripetal force. Where K equal 4 pp0 in mks units, m is the mass of the electron, and v is its velocity. From assumption 3 we have: since n takes on integral values, r should be denoted by Rn to indicate the nth orbit. Then eq 2.7 can be written. Substituting eq 2.8 in eq 2.6, we find that for the radius of the nth orbit of the electron. Now we must find the expression for the total energy of the electron in this orbit, so that we can calculate the energies involved in transitions between orbits. From EQs 2.7 and 2.10, we have: therefore, the kinetic energy of the electron is. The potential energy is the product of the electrostatic force and the distance between the charges. Thus the total energy of the electron in the nth orbit is. The critical test of the model is whether energy differences between orbits correspond to the observed photon energies of the hydrogen spectrum. The transitions between orbits corresponding to the Lyman, Balmer, and Paschen series are illustrated in Fig 2.4. The energy difference between orbits n1 and n2 is given by the frequency of light given off by a transition between these orbits is. The prefactor is essentially the Rydberg constant r times the speed of light c. A comparison of EQ 2.17, with the experimental results summed up by EQ 2.3, indicates that the Bohr theory provides a good model for electronic transitions within the hydrogen atom, as far as the early experimental evidence is concerned. Whereas the Bohr model accurately describes the gross features of the hydrogen spectrum, it does not include many fine points. For example, experimental evidence indicates some splitting of levels in addition to the levels predicted by the theory. Also, difficulties arise in extending the model to atoms more complicated than hydrogen. Attempts were made to modify the Bohr model for more general cases, but it soon became obvious that a more comprehensive theory was needed. However, the partial success of the Bohr model was an important step toward the eventual development of the quantum theory. The concept that electrons are quantized in certain allowed energy levels, and the relationship of photon energy and transitions between levels, had been established firmly by the Bohr theory. The principles of quantum mechanics were developed from two different points of view at about the same time, the late 1920s. One approach, developed by Heisenberg, utilizes the mathematics of matrices and is called matrix mechanics. Independently, Schrödinger developed an approach utilizing a wave equation, now called wave mechanics. These two mathematical formulations appear to be quite different. However, closer examination reveals that beyond the formalism, the basic principles of the two approaches are the same. It is possible to show, for example, that the results of matrix mechanics reduce to those of wave mechanics after mathematical manipulation. We shall concentrate here on the wave mechanics approach, since solutions to a few simple problems can be obtained with it, involving less mathematical discussion. Probability and the uncertainty principle. It is impossible to describe with absolute precision events involving individual particles on the atomic scale. Instead, we must speak of the average values, expectation values, of position, momentum, and energy of a particle, such as an electron. It is important to note, however, that the uncertainties revealed in quantum calculations are not based on some shortcoming of the theory. In fact, a major strength of the theory is that it describes the probabilistic nature of events involving atoms and electrons. The fact is that such quantities as the position and momentum of an electron do not exist apart from a particular uncertainty. The magnitude of this inherent uncertainty is described by the Heisenberg uncertainty principle. In any measurement of the position and momentum of a particle, the uncertainties in the two measured quantities will be related by similarly, the uncertainties in an energy measurement will be related to the uncertainty in the time at which the measurement was made. By these limitations indicate that simultaneous measurement of position and momentum or of energy and time is inherently inaccurate to some degree. Of course, Planck's constant h is a rather small number, 6.63 * 10 to 34 J at s, and we are not concerned with this inaccuracy in the measurement of x and px for a truck, for example. On the other hand, measurements of the position of an electron and its speed are seriously limited by the uncertainty principle. One implication of the uncertainty principle is that we cannot properly speak of the position of an electron, for example, but must look for the probability of finding an electron at a certain position. Thus, one of the important results of quantum mechanics is that a probability density function can be obtained for a particle in a certain environment, and this function can be used to find the expectation value of important quantities such as position, momentum, and energy. We are familiar with the methods for calculating discrete, single-valued, probabilities from common experience. For example, it is clear that the probability of drawing a particular card out of a random deck is 1/52, and the probability that a tossed coin will come up heads is 1/2. The techniques for making predictions when the probability varies are less familiar, however. In such cases it is common to define a probability of finding a particle within a certain volume. Given a probability density function p, x, for a one-dimensional problem, the probability of finding the particle in a range from x to x plus dx is p, x, dx. Since the particle will be somewhere, this definition implies that if the function p, x, is properly chosen. Equation 220 is implied by stating that the function p, x, is normalized, i.e., the integral equals unity. To find the average value of a function of x, we need only multiply the value of that function in each increment dx by the probability of finding the particle in that dx and sum over all x. Thus the average value of f, x, is. If the probability density function is not normalized, this equation should be written. The Schrödinger wave equation. There are several ways to develop the wave equation by applying quantum concepts to various classical equations of mechanics. One of the simplest approaches is to consider a few basic postulates, develop the wave equation from them, and rely on the accuracy of the results to serve as a justification of the postulates. In more advanced texts these assumptions are dealt with in more convincing detail. Basic postulates. 1. Each particle in a physical system is described by a wave function degree, x, y, z, t. This function and its space derivative, 0/0x plus 0/0y plus 0/0z, are continuous, finite, and single-valued. 2. In dealing with classical quantities such as energy E and momentum p, we must relate these quantities with abstract quantum mechanical operators defined in the following way. And similarly for the other two directions. 3. The probability of finding a particle with wave function degree in the volume dx dy dozen is degree dx dy dozen 2. The product degree is normalized according to EQ 220, so that L dx dy dozen equal 1 and the average value 8q9 of any variable q is calculated from the wave function by using the operator form cop defined in postulate 2, 8q9 equal L, cop dx dy dozen. Once we find the wave function degree for a particle, we can calculate its average position, energy, and momentum, within the limits of the uncertainty principle. Thus, a major part of the effort in quantum calculations involves solving for degree within the conditions imposed by a particular physical system. We notice from assumption 3 that the probability density function is. The classical equation for the energy of a particle can be written: kinetic energy plus potential energy equal total energy. In quantum mechanics we use the operator form for these variables. Postulate 2, the operators are allowed to operate on the wave function degree. For a one-dimensional problem EQ 222 becomes 3, which is the Schrödinger wave equation. In 3 dimensions the equation is: the wave function degree in EQs 223 and 224 includes both space and time dependencies. It is common to calculate these dependencies separately and combine them later. Furthermore, many problems are time independent, and only the space variables are necessary. Thus we try to solve the wave equation by breaking it into 2 equations by the technique of separation of variables. Let degree, x, t, be represented by the product E, x, h, t. Using this product in EQ 223, we obtain. Now the variables can be separated to obtain the time-dependent equation in one dimension, and the time-independent equation. See, 2um2d dx 2 plus v, x, de, x, equal e, x, 226b. This type of equation, where an operator operating on a function equals a constant times the function, is known as an eigenvalue equation. From the German word eigen meaning proper, we can show that the separation constant E corresponds to the total energy, kinetic plus potential, of the particle. We get different eigenfunctions Cn corresponding to different eigenenergies, En. Since the time-dependent equation, 226a, is a first-order differential equation, its solution is simply f, t, equal exp, jeut, equal exp, jvt. Using the Planck relation. This form is the universal time dependence of all eigenfunctions. We can show in quantum mechanics that any arbitrary wave function can be written as a linear combination of these eigenfunctions, with prefactors or weighting coefficients that depend on the initial conditions. As an analogy, remember that an arbitrary vector, v, can be expanded as a linear combination in terms of unit vectors or basis vectors along the x, y, and z axes, with coefficients. A wave function can similarly be written as a linear combination of various eigenfunctions, with appropriate prefactors, each evolving in time, as shown above. Hence, eigenfunctions are sometimes also known as basis functions. But unlike real vectors expandable in terms of 3 basis vectors in real space, these eigenfunctions span an infinite number of dimensions in an abstract space known as Hilbert space. If we measure the energy of the particle, we will get one of these eigenenergies with a probability given by Cn2. If we keep repeating these measurements, each time we get a different eigenenergy with corresponding probabilities, Cn2. This leads to the famous uncertainties in quantum mechanics. The average of many quantum mechanical measurements will correspond to the classical physics result. These equations are the basis of wave mechanics. From them we can determine the wave functions for particles in various simple systems. The only thing that changes from one quantum mechanical problem to the other is the form of V, x. For calculations involving electrons, the potential term V, x, usually results from an electrostatic or magnetic field. 2.4.3 Potential well problem. It is quite difficult to find solutions to the Schrödinger equation for most realistic potential fields. One can solve the problem with some effort for the hydrogen atom, for example, but solutions for more complicated atoms are hard to obtain. There are several important problems, however, which illustrate the theory without complicated manipulation. The simplest problem is the potential energy well with infinite boundaries. Let us assume a particle is trapped in a potential well with V, x, 0 except at the boundaries x equals 0 and L, where it is infinitely large, Fig 2.5a. Inside the well we set V, x, equals 0 in EQ. 226b. This is the wave equation for a free particle. It applies to the potential well problem in the region with no potential V, x. Possible solutions to EQ. 229, are sin kx and cos kx, where k is 2 MeU. In choosing a solution, however, we must examine the boundary conditions. The only allowable value of E at the walls is 0. Otherwise, there would be a non-zero E2 outside the potential well, which is impossible because a particle cannot penetrate an infinite barrier. Therefore, we must choose only the sign solution and define k such that sin kx goes to 0 at x equal L. The constant A is the amplitude of the wave function and will be evaluated from the normalization condition, postulate 3. If E is to be 0 at x equal L, then k must be some integral multiple of r/L. From EQs 230 and 231, we can solve for the total energy En for each value of the integer n. Thus for each allowable value of n the particle energy is described by EQ. 233. We notice that the energy is quantized. Only certain values of energy are allowed. The integer n is called a quantum number, the particular wave function En and corresponding energy state En describe the quantum state of the particle. The quantized energy levels described by EQ. 233, appear in a variety of small geometry structures encountered in semiconductor devices. We shall return to this potential well problem, often called the particle in a box problem, in later discussions. The constant A is found from postulate 3. The first three wave functions E1, E2, and E3 are sketched in Fig 2.5b. The probability density function E*, or E2, is sketched for E2 in Fig 2.5c. Another useful form of the potential is V, x, equal kx2, a parabolic potential well, which corresponds to the simple harmonic oscillator, show. The shape of the wave functions and the eigenenergies are obviously going to be different from the rectangular potential well above. The eigenenergies in this case are found to be equally spaced, and given by En equal, n plus 1 greater than 2, uv for various positive integer values of n, corresponding to n quanta of these show. In Chapter 3, we will discuss elastic waves in a lattice due to simple harmonic oscillations of atoms in a parabolic interatomic potential, whose quantized units are known as phonons, in analogy with the photons we discussed above. The energy of these phonons is given by uv. Given a plane wave E equal aexp, jkxx, what is the expectation value for example 2px, the x component of momentum? This is the de Broglie relationship. If we try to evaluate these integrals directly, we run into the problem that both numerator and denominator tend to infinity, because an ideal plane wave is strictly not a normalizable wave function. The trick to use is to choose the limits of integration from, say, L2 to plus L2 in a region of length L. The factor L cancels out in the numerator and denominator. Then we can consider L approaches infinity. For wave functions that are normalizable, such a mathematical trick does not have to be used. If we include the time dependence also, we get equal AEXP, JKXXJVT. We can also calculate the expectation value of the energy operator. After normalization, which is the Planck relation. Tunneling. The wave functions are relatively easy to obtain for the potential well with infinite walls, since the boundary conditions force E to 0 at the walls. A slight modification of this problem illustrates a principle that is very important in some solid-state devices: the quantum mechanical tunneling of an electron through a barrier of finite height and thickness. Let us consider the potential barrier of Fig 2.6. If the barrier is not infinite, the boundary conditions do not force E to 0 at the barrier. Instead, we must use the condition that E and its slope d dx are continuous at each boundary of the barrier, postulate 1. Thus E must have a non-zero value within the barrier and also on the other side. Since E has a value to the right of the barrier, E** exists there also, implying that there is some probability of finding the particle beyond the barrier. We notice that the particle does not go over the barrier, its total energy is assumed to be less than the barrier height V0. The mechanism by which the particle penetrates the barrier is called tunneling. However, no classical analog, including classical descriptions of tunneling through barriers, is appropriate for this effect. Quantum mechanical tunneling is intimately bound to the uncertainty principle. If the barrier is sufficiently thin, we cannot say with certainty that the particle exists only on one side. However, the wave function amplitude for the particle is reduced by the barrier, as Fig 2.6 indicates, so that by making the thickness W greater, we can reduce E on the right-hand side to the point that negligible tunneling occurs. Tunneling is important only over very small dimensions, but it can be of great importance in the conduction of electrons in solids, as we shall see in chapters 5, 6, and 10. A novel electronic device called the resonant tunneling diode has been developed. This device operates by tunneling electrons through particle in a potential well energy levels of the type described in section 2.4.3. The Schrödinger equation describes accurately the interactions of particles with potential fields, such as electrons within atoms. Indeed, the modern understanding of atomic theory, the modern atomic models, comes from the wave equation and from Heisenberg's matrix mechanics. It should be pointed out, however, that the problem of solving the Schrödinger equation directly for complicated atoms is extremely difficult. In fact, only the hydrogen atom is generally solved directly. Atoms of atomic number greater than 1 are usually handled by techniques involving approximations. Many atoms, such as the alkali metals, Li, Na, etc., which have a neutral core with a single electron in an outer orbit, can be treated by a rather simple extension of the hydrogen atom results. The hydrogen atom solution is also important in identifying the basic selection rules for describing allowed electron energy levels. These quantum mechanical results must coincide with the experimental spectra, and we expect the energy levels to include those predicted by the Bohr model. Without actually working through the mathematics for the hydrogen atom, in this section we shall investigate the energy level schemes dictated by the wave equation. The hydrogen atom. Finding the wave functions for the hydrogen atom requires a solution of the Schrödinger equation in 3 dimensions for a Coulombic potential field. Since the problem is spherically symmetric, the spherical coordinate system is used in the calculation, Fig 2.7. The term v, x, y, z, in EQ 224, must be replaced by v, r, u, h, representing the Coulomb potential which the electron experiences in the vicinity of the proton. The Coulomb potential varies only with r in spherical coordinates as in EQ 214. When the separation of variables is made, the time-independent equation can be written as thus: the wave functions are found in three parts. Separate solutions must be obtained for the r-dependent equation, the u-dependent equation, and the f-dependent equation. After these three equations are solved, the total wave function C is obtained from the product. As in the simple potential well problem, each of the three hydrogen atom equations gives a solution which is quantized. Thus we would expect a quantum number to be associated with each of the three parts of the wave equation. As an illustration, the f-dependent equation obtained after separation of variables is, where m is a quantum number. The solution to this equation is, where a can be evaluated by the normalization condition, as before. Thus the value of a is, and the f-dependent wave function is. Since values of h repeat every 2r radians, should repeat also. This occurs if m is an integer, including negative integers and 0. Thus the wave functions for the h-dependent equation are quantized with the following selection rule for the quantum numbers. By similar treatments, the functions r, and w can be obtained, each being quantized by its own selection rule. For the r-dependent equation, the quantum number n can be any positive integer, not 0, and 4. The u-dependent equation, the quantum number L can be 0 or a positive integer. However, there are interrelationships among the equations which restrict the various quantum numbers used with a single wave function. These restrictions are summarized as follows. In addition to the three quantum numbers arising from the three parts of the wave equation, there is an important quantization condition on the spin of the electron. Investigations of electron spin employ the theory of relativity as well as quantum mechanics. Therefore, we shall simply state that the intrinsic angular momentum s of an electron within Lm specified is. That is, in units of u, the electron has a spin of 1, 2, and the angular momentum produced by this spin is positive or negative depending on whether the electron is spin up or spin down. The important point for our discussion is that each allowed energy state of the electron in the hydrogen atom is uniquely described by four quantum numbers, n, l, m and s. For using these four quantum numbers, we can identify the various states which the electron can occupy in a hydrogen atom. The number n, called the principal quantum number, specifies the orbit of the electron in Bohr terminology. Of course, the concept of orbit is replaced by probability density functions in quantum mechanical calculations. It is common to refer to states with a given principal quantum number as belonging to a shell rather than an orbit. There is considerable fine structure in the energy levels about the Bohr orbits, due to the dictates of the other three quantum conditions. For example, an electron with n equal 1, the first Bohr orbit, can have only L equal 0 and M equal 0 according to EQ 246, but there are two spin states allowed from EQ 247. For n equal 2, L can be 0 or 1, and M can be -1, 0, or +1. The various allowed combinations of quantum numbers appear in the first four columns of Table 2.1. From these combinations it is apparent that the electron in a hydrogen atom can occupy any one of a large number of excited states in addition to the lowest, ground, state C100. Energy differences between the various states properly account for the observed lines in the hydrogen spectrum. The periodic table. The quantum numbers discussed in section 2.5.1 arise from the solutions to the hydrogen atom problem. Thus the energies obtainable from the wave functions are unique to the hydrogen atom and cannot be extended to more complicated atoms without appropriate alterations. However, the quantum number selection rules are valid for more complicated structures, and we can use these rules to gain an understanding of the arrangement of atoms in the periodic table of chemical elements. Without these selection rules, it is difficult to understand why only 2 electrons fit into the first Bohr orbit of an atom, whereas 8 electrons are allowed in the second orbit. After even the brief discussion of quantum numbers given above, we should be able to answer these questions with more insight. Before discussing the periodic table, we must be aware of an important principle of quantum theory, the Pauli exclusion principle. This rule states that no two electrons in an interacting system 5 can have the same set of quantum numbers n, l, m, and s. In other words, only two electrons can have the same three quantum numbers n, l, and m, and those two must have opposite spin. The importance of this principle cannot be overemphasized. It is basic to the electronic structure of all atoms in the periodic table. One implication of this principle is that by listing the various combinations of quantum numbers, we can determine into which shell each electron of a complicated atom fits, and how many electrons are allowed per shell. The quantum states summarized in Table 2.1 can be used to indicate the electronic configurations for atoms in the lowest energy state. In the first electronic shell, n equal 1, L can be only 0 since the maximum value of L is always n, 1. Similarly, m can be only 0 since m runs from the negative value of L to the positive value of L. Two electrons with opposite spin can fit in the C100 state, therefore, the first shell can have at most two electrons. For the helium atom, atomic number Z equal 2, in the ground state, both electrons will be in the first Bohr orbit, n equal 1, both will have L equal 0 and m equal 0, and they will have opposite spin. Of course, one or both of the He atom electrons can be excited to one of the higher energy states of Table 2.1 and subsequently relax to the ground state, giving off a photon characteristic of the He spectrum. Table 2.1 quantum numbers to n equal 3 and allowable states for the electron in a hydrogen atom. The first four columns show the various combinations of quantum numbers allowed by the selection rules of EQ. 246, the last two columns indicate the number of allowed states, combinations of n, l, m, and s, for each L, subshell, and n, shell, or Bohr orbit. As Table 2.1 indicates, there can be 2 electrons in the L equal 0 subshell, 6 electrons when L equal 1, and 10 electrons for L equal 2. The electronic configurations of various atoms in the periodic table can be deduced from this list of allowed states. The ground state electron structures for a number of atoms are listed in Table 2.2. There is a simple shorthand notation for electronic structures which is commonly used instead of such a table. The only new convention to remember in this notation is the naming of the L values, L equal 0, 1, 2, 3, 4, CS, P, D, F, G, C. This convention was created by early spectroscopists who referred to the first four spectral groups as sharp, principal, diffuse, and fundamental. Alphabetical order is used beyond F. With this convention for L, we can write an electron state as follows: 6 electrons in the 3p subshell 3p6, n equal 3, L equal 1. For example, the total electronic configuration for Si, Z equal 1 4, in the ground state is 1s22 s22p63 s23p2. We notice that Si has a closed northeast configuration, see Table 2.2, plus 4 electrons in an outer n equal 3 orbit, 3s23p2. These are the 4 valence electrons of Si, 2 valence electrons are in an s state and 2 are in a p state. The Si electronic configuration can be written northeast 3s23p2 for convenience, since the northeast configuration 1s22 s22p6 forms a closed shell, typical of the inert elements. Figure 2.8a shows the orbital model of a Si atom, which has a nucleus consisting of 14 protons, with a charge of plus 14, and neutrons, 10 core electrons in shells n equal 1 and 2, and 4 valence electrons in the 3s and 3p subshells. Figure 2.8b shows the energy levels of the various electrons in the Coulombic potential well of the nucleus. Since unlike charges attract each other, there is an attractive potential between the negatively charged electrons and the positively charged nucleus. As indicated in EQ 236, a Coulomb potential varies as 1r as a function of distance from the charge, in this case the Si nucleus. The potential energy gradually goes to 0 when we approach infinity. We end up getting particle in a box states for these electrons in this potential well, as discussed in section 2.4.3 and EQ 233. Of course, in this case the shape of the potential well is not rectangular, as shown in Fig 2.5a, but coulombic, as shown in Fig 2.8b. Therefore, the energy levels have a form closer to those of the H atom as shown in EQ 215, rather than in EQ 233. If we solve the Schrödinger equation for the Si atom as we did in section 2.5.1 for the H atom, we can get the radial and angular dependence of the wave functions or orbitals of the electrons. Let us focus on the valence shell, n equal 3, where we have two 3s and two 3p electrons. It turns out that the 3's orbital is spherically symmetric with no angular dependence, and is positive everywhere. It can hold two electrons with opposite spin according to the Pauli principle. There are 3p orbitals which are mutually perpendicular. These are shaped like dumbbells with a positive lobe and a negative lobe, Fig 2.9. The 3p subshell can hold up to 6 electrons, but in the case of Si has only 2. Interestingly, in a Si crystal when we bring individual atoms very close together, the s and p orbitals overlap so much that they lose their distinct character, and lead to 4 mixed sp3 orbitals. The negative part of the p orbital cancels the s-type wave function, while the positive part enhances it, thereby leading to a directed bond in space. As shown in Fig 2.9, these linear combinations of atomic orbitals, LCAO, or hybridized sp3 orbitals point symmetrically in space along the 4 tetragonal directions, see Fig 1.9. In Chapter 3 we shall see that these directed chemical bonds are responsible for the tetragonal diamond or zinc blende lattice structure in most semiconductors. They are also very important in the understanding of energy bands, and in the conduction of charges in these semiconductors. The column for semiconductor GE, Z equal 3,2, has an electronic structure similar to Si, except that the 4 valence electrons are outside a closed n equal 3 shell. Thus the GE configuration is AR3D104S24P2. There are several cases in Table 2.2 that do not follow the most straightforward choice of quantum numbers. For example, we notice that in K, Z equal 19, and Ca, Z equal 20, the 4 state is filled before the 3D state, in Cr, Z equal 24, and cubic, Z equal 29, there is a transfer of an electron back to the 3D state. These exceptions, required by minimum energy considerations, are discussed more fully in most atomic physics texts. 2.1 In classical physics, matter, including electrons, was described as particles by Newtonian mechanics, while light was described as waves, consistent with phenomena such as interference and diffraction of light. 2.2 Phenomena such as blackbody radiation and the photoelectric effect forced Planck and Einstein to introduce a particle aspect to light, photons. Analysis of atomic spectra then led Bohr and de Broglie to analogously introduce a wave aspect to subatomic particles such as electrons. This led to a wave-particle duality and a quantum mechanical description of nature by Heisenberg and Schrödinger. 2.3 To understand how electrons move in semiconductor devices or interact with light, we need to determine a complex wave function of the electron. The wave function has to be mathematically well behaved, consistent with the interpretation that the wave function magnitude squared is the probability density of finding the electron in space and time. 2.4 We get the wave function by solving Schrödinger's time-dependent partial differential equation. The application of boundary conditions, the potential energy profile, allows certain, proper, eigenfunctions as valid solutions, with corresponding eigenenergies, determined by allowed quantum numbers. Results of physical measurements are no longer deterministic, as in classical mechanics, but probabilistic, with an expectation value given by an average using the wave function of appropriate quantum mechanical operators corresponding to physical quantities. 2.5 Application of these principles to the simplest atom, H, introduces 4 quantum numbers n, l, m, and s, which are subject to appropriate quantum mechanical rules. Extrapolating these ideas to more complicated atoms such as Si leads to the idea of electronic structure and the periodic table. If we apply the Pauli exclusion principle that one can have a maximum of one electron for one set of these quantum numbers.